Start recording. Yeah.
Hello everyone, welcome to my channel. I'm Yue Li, and today I invite my supervisor, Professor Robert Mann from University of Waterloo, to ask some questions about black holes. So,
Thank you. Pleasure to be here.
yeah, thank you. So, could you please introduce your research direction? For example, what is black hole thermodynamics and what is black hole chemistry, and why is it important to study them?
I work a lot on black holes, particularly black hole thermodynamics, or what has now come to be called black hole chemistry. And it is a natural outgrowth of the original observations made by Jacob Bekenstein and Stephen Hawking that black holes behave as thermodynamic systems. They can have an entropy that is proportional to the area of the horizon of the black hole and a temperature that is given by the surface gravity at the horizon. These were the theoretical discoveries made in the 1970s by Jacob Bekenstein and Stephen Hawking. And for a long time, black hole thermodynamics really had that as its central feature, plus additional work terms such as the change of charge multiplied by the electrostatic potential if the black hole was charged, or the change in
Mhm.
angular momentum times its angular velocity if it was rotating, and so on. What was missing in black hole thermodynamics for close to 35 years was the notion of pressure and volume, which appears in all other thermodynamic systems that we work with in laboratories. And
Mhm.
so black hole chemistry takes this into account. Black hole chemistry is black hole thermodynamics with pressure. Now, the pressure comes from the vacuum, and in particular, a vacuum with negative cosmological constant behaves as a fluid with positive pressure. This has long been known by cosmologists, but it was only about 15 years ago that people began to take account of it in the thermodynamics of black holes. So it's become important to study this subject because what we've learned from it over the last 15 years is that once you take pressure into account, black holes behave like thermodynamic systems you find in chemistry laboratories.
Mhm.
And it really underscores the perspective that thermodynamics is thermodynamics, whether it's polymers, whether it's water, whether it's electrostatic gels, or whether it's black holes. The
Mhm.
thermodynamics is the thermodynamics.
I see. So you mentioned the pressure, the cosmological constant in black hole chemistry. So usually we treat that is a constant, but why there like a VD term, the variation of the P? So how do we understand that?
Well, yes, normally a cosmological constant is viewed as an arbitrary constant
Mm.
that is fixed. And we simply solve the equations with that in mind. But it can be varied in the sense you can fix it to have any value that you like. And there are a number of ways to do this dynamically. One of them is that the cosmological constant can be regarded as the charge
Mm-hmm.
associated with the generalization of what we call a free-form potential. It's a generalization of the Maxwellian potential in electromagnetism. And
Mm-hmm.
so in that sense, it's a charge analogous to the way electric charge is a charge and can be varied. So certainly that is one way of understanding how you could vary it. But another way of looking at it is that even if you didn't believe it could be varied, by allowing it to vary, you can find that phase transitions of various kinds can occur with black holes.
Mm-hmm.
So, what then matters is the relative size of the fixed constant or the fixed pressure compared to the other thermodynamic variables. And this is what black hole chemistry allows us to take into account. So even if the cosmological constant were fixed, if it is fixed in a certain range of values compared to the other parameters like mass and entropy, you
Mhm.
will indeed see phase transitions that had previously been missed when others studied the subject.
I see. So will the ideal spacetime change when varying the pressure?
Uh, yes, it does change insofar as the cosmological constant changes and the asymptotic structure technically changes.
Mhm.
But as I said earlier, you can regard this as a generalization of the gauge charge. So, in that sense, it's not particularly surprising or mysterious.
So is it a quasi static process when we varying
Well,
the
as with
pressure?
all processes in equilibrium or near equilibrium thermodynamics, yes, you vary the various parameters adiabatically or quasi-statically in order to understand changes, and it would be no different here.
I see. So the next question is about when we discussing black hole thermodynamics. So usually we consider a black hole in thermal equilibrium or non-equilibrium.
Well, the largest fraction of understanding we have about the subject is given by considering states in equilibrium, which really are states where the surface gravity is constant
Mhm.
or where it is not changing very much or very quickly. So, an evaporating asymptotically flat black hole will lose energy as it evaporates, lose
Mhm.
mass, and therefore its surface gravity will slowly change. But the general view or understanding is that if it doesn't change too quickly, it's an approximate thermodynamic equilibrium, and we can understand that. In the case of anti de Sitter black holes, the nature of anti de Sitter space is such that radiation coming out is reflected back from infinity. And so
Mhm.
the black hole can be in equilibrium with its own radiation. And therefore, we don't even have to approximate it as being an equilibrium. It really is an equilibrium.
I see. Thank you for the sharing on black hole thermodynamics. So goodbye.
Bye bye.